Welcome back to the 3:30 session. I hope the coffee was good. I want to invite Ari and Zach to tell us about miniDusa, logic programming, very near and dear to my heart, so I'm excited to hear about it.
Awesome. Thanks so much. Hey, everyone. I'm Zach.
I'm Ari.
And we are both undergrads at Northeastern, and today we are going to be talking to you about miniDusa, an extensible finite-choice logic programming language. But before we can talk about miniDusa, I think it is worthwhile to talk about Dusa. So this is a logic programming language that was implemented by Rob, who's here today. And there was a recent POPL paper about this, and the website to go try this out, Dusa Rocks, is up there. You should totally try it because Dusa rocks. It's in the URL. Dusa is a logic programming language similar to Datalog. So we'll start by sort of walking through an example there. So like in Datalog, programs consist of facts, which are known information, and rules that allow you to deduce new facts from existing facts. So as an example, if we have this graph here with 5 nodes, we can encode this as a handful of these edge relations here. So here, edge is a relation that says 2 nodes are related. So this represents an edge from node A to node B, an edge from node B to node C. And then this second rule here says whenever there is an edge from a node Y to X, we have the corresponding edge going the other direction. So this is ensuring that our graph is undirected. Once we have encoded this graph in Dusa, we can then perform some computations on this graph. So a classic program that one can write is computing which nodes are reachable from which other nodes. So if there's an edge between 2 nodes, X and Y, then obviously you can reach Y from X. And similarly, if 2 nodes are reachable, and then there's another edge that sort of tacks on, that is reachable as well. Then running this program will give a solution, right? It will compute all of the facts that we possibly can, and it will tell you which nodes can reach which other nodes, right? Node A can reach itself, reach node B, reach node C, and a bunch more facts that we don't have on the slide. Cool, so that's like classically how Datalog works, but Dusa, unlike Datalog, solutions can have, computing a Dusa program can give you multiple different solutions, like a big set of solutions, each containing different facts. And the way that we can get solutions with different facts is by making choices. So Dusa has a mutually exclusive choice primitive in the language that allows you to associate one of multiple choices. So for example here, we have a handful of edges and nodes facts just from earlier, and this new rule says whenever we have some node X, assign it one of 3 different colors, red, green, or blue. So this will go and sort of assign a color to every single node in our graph, and our solutions will contain all of this information. Notably, these are mutually exclusive choices, so in any one particular solution, each node only maps to a specific color, like A is red, B is blue. So if you visualize these, we can see there are a bunch of solutions. In fact, here there are 5 to the 3rd of them, right? We have 5 nodes and 3 colors for each. So this isn't a very interesting program, but we can add a constraint here to ensure that we are only computing the valid 3 colorings of this graph. So specifically, we want to throw away all of the solutions where there are 2 nodes connected by an edge that have the same color. So this C here is some logic variable, and this says if node X has the same color as node Y, then throw those away. And so this ensures that we only ever get out valid 3 colorings. So then there are, instead of 5 to the 3rd solutions, there's like 72 of them. And this is like a nice, convenient way to compute all of these. One last type of rule in Dusa that I think is worth going through is what are called open rules. So we just saw an example of ways that we can sort of make choices on a node-by-node basis. Perhaps we want to make another choice here, like the color of node A could be either red or yellow. But this sort of runs into the fact that all of our choices here, they have to sort of, we can only make one choice per node here, right? If this rule gave us color green and this rule gave us color yellow, those can't both coexist, and so the solution there sort of like gets thrown away. So the only way that this rule actually tells us anything is it restricts us to only ever assigning the color red to the node A. So to get around this, we introduce a notion of open rules, which are written with this question mark. So this is sort of representing a choice that can be made. It does not have to be made. So we can select one of red, green, or blue for an arbitrary node. But for A specifically, we're going to pick definitely red or yellow. And so we can see both of these possibilities here. And then finally, like if both of these were these open rules, then we have the option to pick red, green, or blue. We have the option to pick red or yellow. One of them is always going to be picked, and we can see we have a bunch of different possible solutions there. Okay, so that was a little bit about Dusa. Now I think it is time for us to talk about what we have done, which is miniDusa. This is a re-implementation of Dusa in Racket using the syntax-spec metalanguage, which allows us to get a lot of interesting things from the Racket ecosystem sort of for free. So let's first sort of take a look at this example that we've seen and translate it into miniDusa. So as you can see, it looks basically the same, but with more parentheses now. I know everyone was getting concerned at the lack of those. Here, this is basically the same program, and if we wanted to solve it and get out a big stream of solutions, there's a solve function that takes one of these programs and computes the solutions there. So let's take a look at this program in Dr. Racket. So one thing that we can see here is we have these edge and node facts. If I can move my cursor over, that would be great. Can I move my cursor over? Yes, I can. Awesome. Okay. So one thing that is useful to see here that we sort of get for free from syntax-spec is IDE integration and binding structure. So here, if we highlight a relation name like edge, we can see that they all sort of like highlight with the little arrows too. So like X here, we can see each of the bound occurrences of logic variables, which is nice. This is great. And then if we go and we click the run button, we can see, if I click onto the right tab, Dr. Racket, cool. We can see that there are in fact 72 solutions, and here is the first one that it happened to generate. This looks like a 3 coloring because A and B and C have different colors, and sure, cool. If we go back to Keynote, that would be great. My cursor is definitely on the wrong slide. Sorry. Okay, cool. So we are going to be talking a little bit about what we get out of this architecture and why it's cool that we've embedded this into Racket as a DSL. And so let's look at like an overview of how this sort of works. So as some people here might know, and as Michael will talk about tomorrow, the syntax-spec metalanguage allows us to equip a domain-specific language with a hygienic macro system. So users can write miniDusa macros, not just Racket macros, which then get expanded into this core syntactic form. And this is the core form on which all static checks are applied, right? You can make sure that each relation in your program is used with the right number of arguments, that all of your variables are bound in the right places. Syntax-spec helps out with that. Then we sort of compile this down to some like Racket representation of our data, and we can throw that at our solver. Our solver is pretty naive. That's sort of the mini part of this. Yes. So in addition to sort of getting this nice macro extensibility from syntax-spec, we also get good opportunities for interacting with Racket, doing this sort of language-oriented programming stuff that we also sort of get from being an embedded DSL. So to demonstrate this, we're sort of going to take a look at a recurring example here, which is a program that demonstrates Dusa's applications to support creative practices. This was a big reason why Dusa was created in the first place. So here we're going to be looking at an example program that generates worlds for a small video game, perhaps. So here we have facts that are defining a 5x6 grid, right? We have each, the x and the y, and then we pair them together to get coordinates. We then have a relation adjacent, which computes which coordinates are next to each other, right? 2 coordinates are next to each other when they vary by exactly 1 in either the x or the y component. And the fact that we we have this adjacent fact which tells us which sort of rows and columns are next to each other, sort of hard-coded. So like in the graph coloring example, we will assign one type of terrain to each coordinate on the grid, a city, a forest, a mountain, and then we add some constraints. Perhaps if this was a game and you spawn in a city, you'd like there to be at least one city. So we can demand that there is at least one city. And similarly, perhaps two cities shouldn't be adjacent to one another, and so we can forbid that as well with a rule. And finally, as an example, we can say that all of our cities in our world should be able to reach water, reach the ocean, without having to cross over mountains. And so we define, obviously, the ocean can reach the ocean, and we have the option of being able to reach water if we are adjacent to something that can reach water. But of course, if we are having to cross through a mountain to get there, then we shouldn't be considering that. And so our final constraint on this program is that all of our cities have to be able to reach water. If we ever have a city that cannot reach water, we throw away that solution. And we can run this program and see it spins for a little bit and gives us an example here. There's forests, there's cities. It happened to generate a bunch of forests and cities, but mountains and oceans and stuff, they come around too. Okay, cool. So I am going to hand this over to Ari, who is going to be sort of adding features, exploring miniDusa's features, and sort of rewriting this program to be show off some of the cool things that we can do.
Okay, there we go. Yes, so we saw features that were effectively in plain Dusa, and we want to talk about things that we have added to it that we were able to add as a consequence of having syntax-spec. And one of the first things that we were able to do is interoperate with Racket much more than Dusa would be able to interoperate with its host language. And Dusa does this by having a bunch of built-in relations like adding numbers, multiplying, string concatenation, etc. that are hard-coded into the language, but we allow importing arbitrary Racket functions as our own relations. And so we take a language-oriented approach here. So some things you can imagine are much better implemented in logic programs. Some are better represented in functional programs, or other Racket hash lines. And as long as you can express it as a function, and that function is pure, and we can use it in miniDusa. Here we have imported the add1 function from Racket as s for successor, and same thing with the less than or equal to function. And this allows us to actually work with numbers in a more reasonable way. We can use, this program will compute, will count numbers. So we can start with 1, then because add1 of 1 is 2, we go to 2, 3, 4, and 5. And then we can't deduce any more facts. And we can see how this example applies, importing applies to our previous example. Mouse. Okay, yes. We have imported the, where is the, here you can see we've imported the add1 function as the successor. And if you look at it being used, we can, instead of having to list out a bunch of adjacency numbers, which are just 0, 1, 1, 2, etc., we can actually see which numbers should be adjacent to each other in a much, in a more logical way. Well, okay. Yes, and you can also see if we want to use a bracket function like adjacent, this is much easier to express in Racket than it is in a as a bunch of logic rules, and we can use the adjacent function and import it into our miniDusa program, and with a very small modification to check that the value is actually returned to be true instead of just like the relation holds, we can like interoperate with the host language. Okay. And more features that we have included in miniDusa are macros, which again comes from syntax-spec. We get hygienic macros for free effectively, and we are able to express facts in a much more like, wow, sorry. We're able to express things in a much more convenient notation. For example, if you have a bunch of these facts, this gets annoying to write if you have a big graph. You can imagine that you want to write it in a more familiar, like adjacency list style notation, and this would expand out into exactly these facts, as we can see. Yeah, so this is like a normal Racket macro. It doesn't really matter what it does. Yes, we declare the edge relation, and you can see that the binding structure just works thanks to syntax-spec. We know that we're feeding it that relation. It writes a bunch of facts with that relation, and we can use it in here, and it works exactly the same. And Dusa had forbid and demand rules that we also have implemented as macros. They're just much more convenient to work with as a language implementer than having to hard code these into the language itself. And thanks to hygiene, we can generate fresh relation names for free. Like OK is just like local to this scope. And I didn't explain this earlier. Decals is just it's just a container, so we can expand into more than one thing. Forbid is going to say OK. OK is true, so it has to be true. But if these premises are holding, then OK is false. And if OK is true and OK is false both get derived, then we throw away the solution. Same thing with demand, except we do the opposite thing. We start off with it being false, and we say it's true if these premises hold, and if they don't, we throw away the solution. A nice thing with macros is that they let you abstract over the encoding of something. You can imagine that if you use a macro, and the macro can effectively do what it wants, as long as it gives you a bunch of relations in the way that you expect them, it doesn't matter what it does. Okay. Yeah, you can see that if we define a macro that gives you the grid relation, it effectively does the same thing that we did last time, except it's more generic over how many, like what the dimensions of the grid are, that you wouldn't have to write out manually. And yeah, we invoke the grid macro, and we say these are the coordinates. This is not working. So, okay. Collaborative. Yeah, it does that sometimes. Anyway, we use the grid macro that gives us a bunch of facts that are the coordinates of the grid, and like none of this had to change here. The really cool thing is we can change how the grid macro is implemented. like if we swap it out to this secret macro, that I should be able to expand it. If this works, whatever. It's not his. Yes, it does a different thing. It computes the same facts, except it actually is able to, the macro imports its own versions of add one and less than in case, like, you might not have done that here. The macro can import its own things for its own purposes. And we compute, starting from 0, 0, we compute the rows and the columns, and we like build out from there. You can imagine like trade-offs between this and that. One of them might be faster for the implementation. One of them has more facts. One of them has more rules that you have to keep going and deduce. And depending on whichever one makes more sense to you, you want to use that one. Okay. Another like that's about it for this example, the big like world generation example. But we want to talk about one more feature that we have in Dusa or miniDusa is that we have external relations. And because sometimes you want to have a logic program that has to actually interoperate with facts known from outside, like you might just want to have like pull in facts from a database, from the internet, or what have you, and run some computation on those facts and decide something. And here you can see that we have like names and birthdays, for example, and like you can imagine this data comes from somewhere that is not the file. I am a mouse. Yes. But we're using the Gregor, the date parsing library for dates, and we can just write a Racket function to check if two people were born in the same year, and we can use that in miniDusa as if it were just a relation. And you can imagine like the setup for this is that you want to put people into rooms to run a study, and those people have to have different like birth years or like different ages, whatever. And you can imagine that these facts, they're just getting converted into a set of facts from our function that's like barely off screen. Yes. Yeah, we're taking this list and we're converting it into a format that miniDusa understands, and we can and you can just, like, this is just effectively running miniDusa as a subroutine over like external facts. So that is about it for the current state of miniDusa, and we want to talk about future work. Like the current ways to interact with miniDusa is somewhat limited, and you want to make sure that there are easier ways to pass in data from Racket and interact with the program's output using a like better API than just to like look at a bunch of facts. And our main thing is performance. miniDusa is pretty slow compared to like regular Dusa, and we want to make that be less the case. And we also want better syntactic sugar. Like we love parentheses, but there's sometimes too many parentheses for our liking. Yeah, that's about it. We have any questions?
Questions for our speakers?
What was your experience using syntax-spec? What was good and what was bad?
Yeah, I think overall using syntax-spec was very positive. Some things were way easier than we expected them to be. Basically, everything that interacted with the macro system and with hygiene sort of worked on our mostly first try, which certainly would not have been the case without syntax-spec. There are some interesting limitations that we sort of ran into. One interesting thing is that the binding structure of our program is a little bit interesting, right? We have our logic variables, which are bound on like a per rule basis, and we also have our relation variables, which are bound on a per program basis. And so getting syntax-spec to sort of export those in the correct ways was a little bit tricky and required a little bit of massaging of the syntax using some rewrite rules and also grabbing some stuff in from EELib to make that actually work. So, but for the most part, it was very pleasant.
Cool.
Because I know you know some of the Dusa developers, what did they think about the design and trade-offs, and especially the host-laying interaction part?
We talked to them a few times. I think they generally like it. Yeah.
Well, that's a good answer.
It's just
When you ask for a solution, it's a random solution among all the possibilities. Is that right?
Yes, but currently no. We turn that off so that way things like were more predictable. But yeah, we
Normally, yeah.
we randomly can generate them. Yeah.
Do you worry about picking uniformly across the space of possibilities, or do you just do whatever a backtracking search might give you?
Currently, we basically just do whatever backtracking search might give us. In actual Dusa, I believe that search will sort of like go back to the start a little bit to hope to explore different paths. That way you don't like generate a ton of solutions that are like very similar to each other in bunches. I think there's a lot of design space for tweaking that on a like program by program basis. But,
Cool. And do you see syntax-spec as helping with that aspect and maybe doing optimizations or different ways of compiling it?
So far, we have implemented essentially zero optimizations, but we imagine that if we were to implement optimizations, that syntax-spec would assist us in doing so.
Okay, thanks.
Hi, this is, I think, secretly a question about syntax-spec. So if I remember correctly, you may have hit on a different encoding for forbid and demand than we had, but I think the encoding we had in the paper required a different predicate for every instance of one of the two, either a different OK for forbid or a different OK for demand. Is syntax-spec actually handling creating a new scoped OK?
yes, like every invocation of the macro gets its own like freshly generated OK.
Okay, that's very cool.
Well, does it unblind for you to do that in your JavaScript that you get?
We just directly implemented those in the engine. So was it a translation?
Hello. I'm not particularly familiar with logic programming, but it seems to me like a lot of these things you were implementing as macros are something you would have implemented as a procedure in any other programming paradigm. Is it typical to want to go for macros to implement something like forbid or deny or demand or whatever it's called?
I mean, like, logic programs are fundamentally like a bunch of facts and a bunch of rules, and we don't necessarily have the concept of a function in the same way. And like the closest we have are like functional relations or importing from Racket, which don't really help you throw away solutions in the same way.
Okay, all right. You all are doing this on purpose to bring me happy.
That's a shot.
So going from what was previously asked, is there a way to create a relation in another module and import it into a logic block currently?
No, not currently. But if your relation is like it depends on what kind of relation it is. If it's a function, like yes, it's a function. But if it's like an external relation, it's going to just be effectively a set, and you can bring that set in from anywhere. But we don't currently support having like relations from just like normal surface syntax from another module.
All right, why don't we thank our speakers one more time?